Here's some possible examples of some possible data sets in a study using a two-sample t-test. Um, we actually don't have to worry about what it says up here. This actually doesn't matter. All we need to focus on is the sample means, meaning the mean of sample 1 and the mean of sample 2, and the t-score, because I just want you to see how the t-score changes as the sample means change. So I have 5 possible data sets up here. They're just 5 imaginary data sets. Each one has 2 samples. Um, these numbers could be whatever you want them to be. I think up here I was saying that they're hours of sleep. So right here in sample 1 we have the hours slept per night by these 4 people and the hours slept per night by these 4 people. I think up here I'm saying that these are working college students, 4 working college students and 4 non-working college students. But that actually doesn't matter because we're just focusing on the sample means and the t-scores. So what the mean of sample 1 is if you add these 4 numbers and divide by 4, you get the mean of sample 1. If you add these 4 numbers and divide by 4, you get the mean of sample 2. So the sample means are just sample averages. We can see if the sample means are equal like they are here, then the t-score comes out to 0 because the top of the fraction comes out to 0. If the mean of sample 1 is higher than the mean of sample 2, like it is here, the t-score comes out to a positive number. If the mean of sample 1 is lower than the mean of sample 2, like it is here, the t-score comes out to a negative number. Also, when the t-scores are further apart from each other, I'm sorry, I didn't say that right. When the sample means are further apart from each other, the t-score moves further away from 0. So notice how right here the sample means are 1 apart. 6 and 5 are 1 apart, and the t-score is 0.77. When we go to this data set, the sample means are now 5 apart, because 8 and 3 are 5 apart, and the t-score moves up to 8.66. So as the sample means are getting further apart, the t-score is moving further from 0. Also in this direction, right here the sample means are 2 apart, and t is negative 4.9. But when the sample means are now about 5 apart, like they are here, the t-score moves further from 0, going in the negative direction. So the t-score is affected by how far apart the sample means are. The t-scores are also affected by the standard deviations and the sample sizes. So if the standard deviations are small, meaning if the data doesn't have much spread to it, then that'll also raise the t-score. So S1 is the standard deviation of sample 1. This is measuring how spread out the numbers are in sample 1. S2 is the standard deviation of sample 2. It's measuring how spread out the numbers are in sample 2. If these standard deviations are smaller, that will raise the t-score. Also, if the sample sizes are increased and everything else stays the same, the means and standard deviations don't change, then that'll raise the t-score also. So the t-score tends to get bigger when you use a bigger sample size. So, like I said right here, the t-score is increased by having a larger difference between the means of your 2 samples, having smaller sample standard deviations, or a larger sample size. However, we also have to remember that if the sample means are equal, t will always be 0, because if the sample means are equal, the top of the fraction comes out to 0, and if the top of the fraction is 0, then the entire t-score has to be 0, regardless of what these numbers are on the bottom of the fraction, regardless of what the standard deviations and sample sizes are. So another thing about the t-score is that t-scores further from 0 in either direction are less likely to be found in a situation in which the null hypothesis is actually true. Meaning, if the two populations that you're studying have equal population means, then the t-score of your data set is likely to be somewhere near 0, and t-scores further from 0 are less and less likely in that situation. The reason why is because if the null hypothesis is true and the population means are equal, then the sample means tend to be close to equal, meaning the sample means tend to be closer together and not too far apart. I'm sorry, I meant sample means. So if the population means are equal, the sample means tend to be close to equal, meaning the sample means tend to be not too far apart. And because of that, the t-score tends to be closer to 0. When the sample means are close together, the t-score ends up being close to 0. And since the researcher isn't calculating the population means and can't calculate them, the researcher can't just look at the population means to see if the null is true. If the researcher could calculate the population means, the researcher could just look at them and see if they're equal or unequal. But since the researcher can't do that, and since the population means are unknown, the researcher uses the t-score as a way of deciding if the null hypothesis appears to be true. And the logic is, if the researcher ends up getting a t-score that's far from 0, such as 8.66, and the sample means are pretty far apart, the researcher would think, okay, well, if the null hypothesis is true, then the sample means are usually close together, and my sample means are far apart, which means that if the null hypothesis is true, then it must mean that I found a very unlikely outcome. So my data set is going against the null hypothesis, so I'm going to reject the null hypothesis and conclude that the alternative appears to be true, that the population means appear to be different. Also, if I ended up with an outcome down here at the negative end in which the sample means are far apart, I would think the same thing. I would think if the null hypothesis is true and the population means are equal, then the sample means should have been pretty close together. And since my sample means are pretty far apart, I'm going to reject the null hypothesis, and because my data set is going against what's usually expected when the null is true. So you reject the null hypothesis when your t-score is too far below 0, or when your t-score is too far above 0, because both of those outcomes are unlikely to happen in a situation in which the null is true and the two population means happen to be equal. But if you get a t-score up here at the positive end, you make a different conclusion than you would down here at the negative end. If my sample means were 8 and 3, I would conclude that the mean of population 1 appears to be higher than the mean of population 2, because sample 1 comes from population 1, sample 2 comes from population 2. So if the mean of sample 1 is higher than the mean of sample 2, it suggests that the mean of population 1 is higher than the mean of population 2. So down at this end, I would conclude that the mean of population 1 appears to be higher than the mean of population 2. Down here, it would be the opposite conclusion. Since the mean of sample 2 is higher than the mean of sample 1, it suggests that the mean of population 2 is higher than the mean of population 1. I could also rephrase that. I could say that since the mean of sample 1 is lower than the mean of sample 2, it suggests that the mean of population 1 is lower than the mean of population 2. So either way, you're rejecting the null hypothesis. Out here, if you're far enough to the positive end, you reject the null, meaning you conclude that the population means don't seem to be equal, and you conclude that the mean of population 1 appears to be higher than the mean of population 2. At the negative end, you reject the null hypothesis. You conclude that the population means appear to be not be equal, but you conclude that the mean of population 1 appears to be lower than the mean of population 2. And if you get an outcome with a t-score that's too close to 0, then what that means is that the sample means were too close together to reject the null hypothesis, meaning the sample means are too close together, so the data set doesn't go against the null hypothesis strongly enough to reject it. So what you're going to have is a cutoff t-score at the negative end called a negative critical value. And you're going to have a cutoff at the positive end called the positive critical value. They're just two numbers that can be found in a table. You don't calculate them, you look them up in a table. If the t-score reaches the negative critical value, you reject the null and conclude that the mean of population 1 is lower than the mean of population 2. If the t-score reaches the positive critical value out here, you reject the null and conclude that the mean of population 1 appears to be higher than the mean of population 2. And if the t-score is between the two critical values, you don't reject the null hypothesis, which means the null hypothesis continues to be given the benefit of the doubt. That's if you're between the two critical values. And I also mentioned an idea called a p-value. I won't go into that much detail about what the p-value is right now, but I'll just say that it's calculated by finding the area under a curve, and when the t-score is 0, the p-value is 1. And 1 is the highest that the p-value can possibly be. So when the t-score is at its lowest, the p-value is at its highest. As you move toward the negative critical value, the p-value starts to drop lower and lower. And as you move toward the positive critical value, the p-value drops lower and lower. So t-scores, for every possible t-score has its own p-value, and t-scores further above 0 in this direction have lower and lower p-values. The same thing happens in this direction. T-scores have lower and lower p-values. Once you get to the positive critical value, that t-score has a p-value of 0.05. So once you get to the critical value, the p-value drops down to 0.05. Same thing over here. Once you get to the negative critical value, the t-score reaches down to 0.05 at the negative critical value. And all t-scores beyond the critical value out here have p-values below 0.05 because the p-value keeps getting lower the further you go out here. And all t-scores beyond the negative critical value out here have p-values below 0.05 because the p-value keeps getting lower and lower the further you go out here. So, in other words, if all t-scores between the two critical values have p-values above 0.05, the two critical values have p-values of 0.05, they both have a p-value of 0.05, and all outcomes beyond the critical values have p-values below 0.05.